Hey folks, I thought we'd follow up on an excellent question that Allison asked in Slack about would hot water evaporate at a rate that's differently than cold water? And so when your kids ask questions like this, when you're doing activities in class, science activities, and they ask questions, it's always great to cultivate those question asking skills in them and say something like, I don't know, but let's find out and let's figure out how we can plan that. How could we investigate that question? And so we can do that right now because I want you to get in that habit of asking those questions and modeling that skill for your students to encourage them to ask questions and to figure out how to help them investigate the questions they're asking. So we're out in the shed of science here. Let's look at the temperature. It's a hot day again. It's less than 20% relative humidity and 96 degrees in here. If you can see that on the phone app there. See that it's pretty dry. And so what I've done here, I'm going to switch this around, is I've taken our two thermometers now and I've wrapped them both with gauze. Okay, those are the same two thermometers that we used last time. And one had gauze and one didn't. Now they're both wrapped with gauze. And the temperature's about the same for each of them. It's 34 Celsius. So what I'm going to do is I'm going to heat up some water and have some room temperature water. So one container of water in here is room temperature. So this is presumably about 95 degrees, right? And then I'm going to heat up some other water up close to boiling. So we're going to get the other water closer to, let's say, 200 Fahrenheit. Then we'll soak each thermometer, and we will put them in front of the fan and watch them cool. But this time we're going to look at a graph of them cooling, and we're going to see if we can make sense of that graph afterwards and see which one evaporates more quickly. Okay, so let me pause and get this set up, and then we'll look at the rate of cooling of the hot water on the temperature probe versus the cold water. Should be pretty cool. Okay, first things first, goggles on since we are going to be playing with fire here. Let's turn that on so we can heat up some water in this one flask. And we'll get this going. Got a little boiling flask here. It should heat up pretty quickly. And so this is Pyrex glass, just like you would bake with, right? So it can withstand high temperatures. It's made of something called borosilicate. We're going to heat this water up. It's almost boiling now. And then after it gets hot, I'll set it down, soak the temperature probes in the hot and room temperature water. And then we will go over to the fan and watch them cool off. Okay, so let's put the hot and the cold. Each one each gauze has been soaked in hot or cold. Okay, and I'm going to move them over to in front of the fan. You can see the red one is the one that started out in the hot water, so close to 80 Celsius. And the blue one started out in the room temperature water, so something around 30 Celsius probably. And let's watch them cool off here. In this run it'll collect data here for 3 minutes. So you can see in the graph, you can see the rate at which each one is cooling. So the red one seems to be cooling faster than the blue one, the one that started in the hot water. And over on the right side, you can see the value of each one. So the red one is the one that started in the hot water, and right now it's about 48 Celsius and falling. And the blue one started off in the room temperature water, and it's 23 Celsius and falling. So that's interesting. It looks like, Allison, to answer your initial question, it looks like the hot water starts to cool more quickly, or the rate of cooling is quicker than it is for cool water. And I don't know what that means for our question of if you were going to use your wet sheet in front of the fan technique, if it makes sense to start with hot water on that sheet or cool water. The hot water would cool more quickly, but I still don't know if that it's taking more energy out of the air to do so. That's a good question. It's interesting, although the rates of cooling are different, the hot is definitely cooling more quickly than the room temperature. It looks like they're starting to come together. You can see that the slope, or the rate at which each line is changing, is becoming pretty similar. It's almost like they're converging. I mean, they should end up to be the same temperature eventually. Let's see if that happens by the 3-minute mark. The data is set to collect for 3 minutes, and then it'll stop after then. The graph just rescaled so we can see that. That's why it shifted. And let's see, let's look over at the side. Our temperatures are 27 C for the hot and just under 20 Celsius for the cool. So the hot is still hotter, but it seems to be cooling off faster. Let's see, we've got about 25 seconds left to go on this run. Let's see if they get to the same temperature. That's pretty neat though. So I guess the initial answer is that the hot water cools more quickly than the cool water, but it's still an open question, like I said, as to which takes more energy out of the air. And there we're at the end of our run. And at the end of the run, they ended up being close to the same, but not quite the same. The hot was still hotter. But yeah, I think you can pretty clearly see that the high temperature water cooled down more quickly. It has that steeper slope than the cool water, but both were evaporating. So that's pretty cool. That was a great question, and that's a good example of an I don't know, but let's find out, and then that opens the door to more questions which we might investigate. So always cultivate the kids' questions or anybody's science questions, and then do what you can to investigate those. It's a lot of fun.